Well, good morning, everyone. Welcome to today's webinar, which deals with special purpose control charts in Statgraphics Centurion. It's a fun topic for those of you who are involved in statistical process control and quality control. You're probably used to generating control charts. The ones we're going to talk about today are somewhat unique, a little less standard than you'd come across in the introductory courses you might have taken in statistical process control. But they each have a special purpose and can be actually quite useful. A control chart is basically a plot of a statistic versus time. Now, we often think of control charts being used in manufacturing environments where you might take a sample once an hour, several samples during every shift, and plot that versus time. But actually, control charts are useful in many other circumstances. For example, they're used to monitor medical events, infections in a hospital, and that sort of thing. Basically, any data that's collected over time can be monitored using a control chart. The interesting aspect of a control chart that makes it different than just a simple time plot is that it also contains control limits. Control limits designed to detect unusual values. There are two primary purposes for creating control charts. The first is to determine, based upon some historical data, whether your process has been operating in a state of statistical control. That means that the basic mechanisms and the distribution of whatever data you're looking at hasn't changed. That the process is behaving exactly the same on Monday morning as it is on Friday afternoon. That's typically called a phase one control chart or an initial study. The initial study is the word we use in Statgraphics. The second primary purpose for creating a control chart is to monitor your process. Monitor the process to detect deviations from some standard that you've already established. You may have it come to a agreement with your suppliers and so forth that you will produce a product with a certain mean and a certain standard deviation. In that case, you'd want to use a phase two or a control to standard control chart to in fact monitor that process and be sure that it continues to produce at those pre-established parameters. There are a lot of common control charts that you can find in pretty much every statistical package that deals with quality data. For example, if you're looking at variable data or measurement data, common control charts are things like X bar and R charts, X bar and S charts, moving average charts, EWMA charts, Q sum charts, those sorts of things. Or if you're dealing with attribute data, you'll probably see P or NP charts for proportions, C and U charts for Poisson rates and counts, maybe even P prime and U prime charts for counts that are over dispersed with respect to a binomial and a Poisson process. These are not the charts we're going to be talking about today. These are the charts that I suspect you've seen many times before. What I wanted to talk about and will talk about today are some other types of control charts, less commonly known control charts. In particular, I've picked out 5 types of control charts to talk about. I'll be talking about ARIMA control charts, acceptance charts, Toolwear charts, charts for rare events, and Cuscore charts. Now, I want to invite you, as always, to submit questions via the GoToWebinar facility. And after I've talked for about an hour or so and shown you examples of these 5 types of charts, I'll be happy to answer any questions that have been submitted. So if a question comes to mind, just go ahead, type it into the message box and send it to us, and I'll try to get to as many as I can at the end of the webinar. Now, the first I'd like to show you what the typical model is that most control charts are based on. And we're going to use a little notation. I'm going to let x sub t be a measurement that I've made at time t. The typical model upon which, for example, an x bar chart or an r chart or an s chart is based is that the observation at time t is equal to a mean mu plus a deviation epsilon sub t. That the measurements I collect vary around some process mean, and that the variations, the epsilons, are NID 0 sigma squared. Now, NID 0 sigma squared stands for normally and independently distributed with a mean of 0 and a variance of sigma squared. And I remember Stu Hunter, when I first was learning this, telling us in class that this was basically a litany, NID 0 sigma squared, that we chant over our data, a blessing we give our data, so that the statistical procedures will work properly. There actually are quite a few assumptions in this relatively simple model. We assume, number one, that the process is stationary. That means that the mean and the variance are constant, don't change over time. Secondly, we assume that successive measurements are independent, that there is no correlation or feedback effect, if you like, from one time period to the next. And finally, we assume that there's a normal distribution, that the epsilons in particular, the deviations from the mean, are normally distributed, which makes the original data normally distributed. Now, we're going to relax some of these assumptions as we talk about the special purpose control charts, because not all processes follow this very simple model. Where we're going to start is with a type of control charts called ARIMA control charts. ARIMA control charts are used for data that are serially correlated. And by that I mean where the x sub t's are not independent, where there is some correlation between the observation at time t and the observation at time t plus 1. This is very common, incidentally, if you're taking measurements close together in time, which is becoming more and more common with automatic data collection devices. It's also quite common the data would be serially correlated if you're taking measurements from a continuous process. Imagine measuring the concentration of some chemical process that you're operating where you've got a continuous flow of product. And it's certainly likely that observations taken close together in time will be correlated. Well, that's going to play havoc with a standard Shewhart control chart, so we need to do something about that. Now, I have a data set. It's actually a data set out of the famous book on time series analysis by Box and Jenkins, which does measure the concentration of a chemical over a 2-hour period. Let's go over to Statgraphics for a moment, and you'll see I've actually loaded this data into the Statgraphics data sheet. If I was to plot the data versus time, let's just do a simple XY plot. If I put concentration on the y-axis, time on the x-axis, you'll notice there appears to be some dynamic movement in the data. You know, it starts out at around 16.5, goes up for a while, comes down for a while, goes back up for a while. Now, that doesn't necessarily mean that that's an out-of-control process. Okay? There are dynamic processes that have serial correlation between successive observations but are in fact stationary. This process may well have, in the long term, a constant mean and a constant standard deviation. However, the dynamics of the process are such that if you look at it, you do see some natural inherent swings around the process mean. Now, what would happen if we tried to do a standard, let's say, X chart on this data? If I go to SPC control charts, basic variables charts, let's say individuals, and tell it to create an individual's chart of the observations versus time, what we're going to see is quite a few signals appear on the X chart. And here's a standard X chart. Actually, it created an X chart and a moving range of 2. But on the X chart, you can see the mean of the process. You can see the control limits at plus and minus 3 standard deviations. And you can see quite a few signals. There's a point below the lower control limit here, a couple points above the upper control limits here, and a lot of runs rules violations. All these little red asterisks are violations of some runs rule, such as 8 in a row, 8 points in a row above or below the center line, generating a signal as an unusual event for a random process. Now, the process may well still be in a state of statistical control. It's just that the X chart, which assumes independent measurements from time period to time period, is not appropriate for this sort of data. Now, what we need to do if we have data in which observations are correlated, instead of using a standard X chart, we need to move to what's called an ARIMA chart. An ARIMA chart relaxes the assumption that successive observations are independent. In fact, we will build into the model some dynamics that will explain why there is, in fact, a correlation between observations close together in time. The models we're going to use are the same models that Box and Jenkins popularized for forecasting time series, and those are the autoregressive moving average models. Now, to show you a few autoregressive and moving average models, I've written some of the simpler models on the next couple slides. Here you see 2 pure autoregressive models. Actually, a first order and a second order autoregressive model. The first order autoregressive model says that the observation at time t is equal to a mean plus some multiple of the deviation from the mean in the previous time period plus a random component. Okay, now the random component Box and Jenkins like to think of as being shocks to the system at a particular point in time. So basically you have the data being equal to a mean plus some function of how far from the mean you were in the previous time period plus a random shock at time t. In the case of the second order model, it's a little bit more complicated. The data at time t are equal to a mean plus multiples of how far you deviated from the mean in the previous 2 time periods plus a random shock. Another class of models are those models called moving average models. In a moving average model, for example, a first order MA1 model, we represent x sub t as being equal to a mean plus a shock that hits our system at time t minus some multiple of the shock to the system in the previous time period. So basically x sub t is equal to mu plus a random deviation at time t minus some multiple of a random deviation in the previous time period. And likewise, an MA2 model looks back at the shocks in the previous period and also in period T-2. We can also put AR terms together with MA terms, and in that case represent XT as, for example, a mean plus an autoregressive component plus an error plus a moving average component. Now, when we model a real set of data, one of the tasks that we're faced with is finding the best model to use. It turns out that the automatic forecasting procedure in Statgraphics is quite useful for helping us build ARIMA models. And I'm going to show you how to do that. I'm going to go back to Statgraphics, and here I have my concentration. I'm now going to go to the top menu to Forecast Automatic Model Selection. This is where I would normally go to forecast future behavior of a time series. But it turns out it's also very good for telling me what sort of ARIMA model to use for a set of data. I'll put in concentration as the data I wish to model, time as the time indices. Where it says number of forecasts, I'm going to put 30. That'll make a nice plot when we're all done. Push OK. On the Analysis Options dialog box, I'm going to turn off all these other sorts of models that the forecasting procedure normally considers, and leave a check mark next to ARIMA models only. I'm going to tell it to try up to second order AR models, second order MA models. But I'm also going to turn off the differencing. I'm going to put a 0 here. Differencing is appropriate if you have a non-stationary process, but in statistical process control, we certainly hope the process is stationary. I'm also going to ask it to include a constant term. Now what it's going to do, it's going to try various combinations of AR-MA models and tell me, according to the selection criteria, which model would be the best. And where it says selection criteria, and I'm going to ask it to find the model with the smallest mean squared error. I'll then push OK, OK again, and you'll see up here that it's selected an ARIMA 101 model. That's shorthand for one autoregressive component, no differencing, and one MA component. It's what I called the ARIMA 101 model on a previous slide. You also see out in front of the last observation, because it is a forecasting procedure, it's forecasted what's likely to happen over the next 30 minutes. Together here with 95% limits. Well, I think I'll go to pane options and change those to 99.73% limits. That makes them like 3 sigma limits. And you can see that for this sort of an ARIMA process, we would expect in a steady state there to be a 99.73% chance of staying within these particular limits. Now, as we'll see in just a moment when I create the ARIMA chart, these bounds here, these 99.73% forecast limits, are one way of putting control limits on these types of processes. Okay, so now we know anyway that an ARMA11 model is a good model to use. At that point, I'm going to go back to SPC control charts, and now you'll notice a section on the control charts menu for special purpose control charts. The special purpose control chart I want to use here is an ARIMA individuals chart. I'll tell it I want to plot observations versus time. On the next chart, it'll allow me, as it does with all control charts, to pick either an initial study or a control to standard. We'll do an initial study. Of more interest here, though, is the section down here where it says model. I'm going to set the model to one AR parameter and one MA parameter. We'll estimate sigma from a moving range of 2. That's the usual way to do it. And I'll ask for a chart of the data with the long-term limits. Okay. And now here you have the final ARIMA chart. The ARIMA chart of the data with a mean plus and minus 3 sigma. The sigma here, though, is larger than it was in the individuals chart. In the individuals chart, the limits went from 16.17 to 17.85. In the ARIMA chart, they go from 15.64 to 18.17. They're wider. They're wider because the dynamics, the correlation in the process, causes the data to wander farther from their mean. But now we have a standard, if you like, 3 sigma control chart that allows for the correlation in the observations. Now, that's one control chart I can do here. It has the long-term limits. So the data with the long-term limits, those forecast limits I showed you in the automatic forecasting procedure. Other useful charts, if I push analysis options, are data with one-step limits. This chart, this form of the ARIMA chart, actually plots each data point and then does forecast limits out in front of the last observation. So it will actually take the most recent observation, forecast one period ahead, and put 3 sigma limits on the one step ahead forecast. What that is sensitive to is shocks that hit the system, large shocks that hit the system at any particular point in time. It's those epsilons you're actually looking at as you look at the difference from one data point to the next. And it's actually here picking out 2 unusual events. There was an unusual event back here where all of a sudden the process went down dramatically, and there's an unusual event here where there was a sudden increase in concentration. So that's very good at detecting unusual one-time events. A similar chart to this one step ahead chart is also a residuals chart. Here I'm actually plotting those epsilons. I'm plotting the random shocks to the system that hit at each point in time. And you can see the 2 signals, same signals as I got on the one step ahead chart, signaling an unusually low shock and an unusually high shock to the system at 2 points in time. Well, that's a very interesting chart, very useful chart, if in fact you have data which are not independent. And there's a lot of data where successive observations, particularly when they're taken close together in time, are not independent. Incidentally, you can also do a standard MR2 chart on the residuals to go with the other control charts, monitoring directly the magnitude of the variability, the sigma, if you like, in the model, to detect, for example, changes in the underlying variability. Okay, well, that's an interesting type of chart. A second chart I want to talk about is something called an acceptance control chart. An acceptance control chart is a control chart that's used to ensure that product remains within specification limits. Now, when we teach the ideas of control charts, we typically emphasize that control charts have nothing to do with specification limits, and usually they don't. The purpose of a control chart is to determine whether a process is in a state of statistical control, whether or not it's stable, or if there are some unusual events that may have occurred that we should know about. However, we can modify the control limits of a standard chart, an X-bar chart, for example, or an X chart, to position the control limits with respect to the specifications rather than with respect to the process mean. And use that chart, it will look like a control chart, not strictly for control, but to detect situations when the data are getting too close to the specification limits. Now, an acceptance control chart is going to be a very useful chart, particularly if you have a high CPK process. Now, a high CPK means that the data, the measurements that you're taking, are very comfortably within the specification limits. For example, here's a plot of what I would call a high CPK process. This is the data where we're measuring the breaking strength of items that are coming from our manufacturing process. You'll notice there is some variability, as there always is whenever we collect real data. On the other hand, the specifications are 200 to 300. So you can see that this particular process is remaining very comfortably within those specification limits. For a process like this, it may not be necessary for that process to be strictly in a state of statistical control. There's room to wander if you like. You know, if the mean went up a little bit or it went down a little bit, we still would not be threatening the specifications. The acceptance control charts that I'm going to talk about will be charts designed to basically let the mean wander as long as we don't get too close to the specification limits. Okay? This, for example, is a picture of a standard X chart on the data, and you'll note that the limits are fairly tight. They go from 231 to 278. Well, let's talk about an acceptance control chart for a moment. How might we design a control chart that takes the specification limits into account? Well, we start by specifying a quantity called F. F will be the maximum allowable fraction of non-conforming items. I start by deciding, you know what, I will be happy with my process if I have no more than, well, let's say 1 out of 10,000 items outside my specification limits. Okay, that's F. We then find the most extreme values of the process mean that would yield no more than F nonconformities. We find some largest allowable value for the mean, we'll call that mu sub u, and some smallest allowable value for the mean, that's mu sub L. Mu sub u will be the upper specification limit minus some multiple of sigma. That z delta is something from a standard normal distribution. and we'll bring ourselves below the upper spec limit just far enough that there won't be any more than F items, F is a fraction, beyond the upper specification limit. Likewise, we'll start at the lower specification limit and add some multiple of sigma. Again, ensuring that we're far enough from the spec that there are no more than F nonconformities. And then we'll base our control limits upon these mu's, mu u and mu l, instead of the overall process mean. That's going to widen out the specifications and actually let the process move a little, as long as it doesn't get too close to the specification limits. Okay, so we'll position the control limits with respect to those extremes. Now, there are two ways that Statgraphics allows you to do this. The first method is to use the sigma multiple method. When we use the sigma multiple method, we construct our control limits by taking the upper allowable mu and adding 3 sigma, and taking the lower allowable mu and subtracting 3 sigma. So basically, we're allowing the process to move between mu sub u and mu sub l, and setting an upper 3 sigma at mu u and the lower 3 sigma limit at mu l. Montgomery, in his book on quality control, calls these modified control limits. A second possible way to do it, and you'll see this option, is to use what's called the beta risk method. In the beta risk method, you start by specifying the beta risk. Beta is the probability of not generating an out-of-control signal when you should. You know, normally if you're doing a standard plus or minus 3 sigma, you're controlling what we call the alpha risk. You're controlling the false alarm probability at about 0.3%. Okay. In the beta risk method, you're controlling the beta risk, the probability of not getting a signal when you should. And in that case, what you do is you put the upper control limit at the highest acceptable mean minus some multiple of sigma, and the lower control limit at mu sub l plus that multiple of sigma, where this multiple of sigma ensures that we will get an out-of-control signal all but beta percent of the time. Beta is the probability of not getting the signal. Okay? Well, let's go to Statgraphics and let's see how this actually works. Let's go back here to Statgraphics, and I'll close off this particular data file. But now I'm going to open a data set called breaking strength. Okay? Breaking strength is sampled once every 10 minutes from a particular process. Well, let's start off by doing a standard X chart. I'm going to go to Control Charts, Basic Variables Charts, Individuals, and ask it to plot strength versus time. Okay. I'm also going to type in now the specification. There's a lower spec of 200, a nominal value of 250, an upper spec of 300, and press OK. Just take all the defaults, and here you'll see the standard X chart. Actually, I'll right-click, go to Pane Options, and ask for the specification limits. So you can see now both the control limits, they go from 231 to 277, and the specification limits 200 to 300. Notice that this process is being fairly tightly controlled relative to that specification. because we are asking, does it have a constant mean? We're not allowing the mean to move at all. Well, you know, if I got a point here or a point down here, I'm probably not in much danger of being out of spec. And these acceptance charts allow me to loosen these control limits somewhat, as long as we don't get too close to the specifications. Now, the way to make an acceptance control chart is to go to SPC, Control Charts, Special Purpose Control Charts. And what I want to do is an acceptance individuals chart. I'll ask it now to plot strength versus time. The spec is 200 to 300. When I press OK, you'll see the analysis options. This is where you see, for one thing, where F is placed. There's a edit field for the fraction non-conforming. That's the maximum number of non-conforming items, maximum fraction of non-conforming items I'm willing to tolerate in this process. And you can see it's set to 1 in 10,000. Up here, you have the choice between using the sigma multiple method and the beta risk method. If you choose sigma multiple method, you'll specify the sigma multiple down here. If you choose beta risk, the field changes to beta risk. Well, let's see what happens if we use the sigma multiple method. Remember now, on the standard X chart, the limits were 231 to 277. If we use the sigma multiple method, the limits will go out quite a bit. The upper control limit will go all the way to 294, and the lower control limit to 205. And we won't signal out of control unless we get a point beyond this upper limit and below the lower limit. Now, if you're really using this to accept product, however, it's probably better to use the beta risk method. The beta risk method says, I want to be sure that all but 5% of the time I will get a signal if I'm producing any more than 1 out of 10,000 items beyond the spec. Okay, so I'm going to switch to beta risk, pick a 5% beta risk, and you'll notice the limits will be somewhat tighter. You'll always find that. If you use that beta risk procedure, they're always tighter than the sigma multiple. But we talked about acceptance sampling last month, and this is very much in line with what we were doing with respect to acceptance sampling. I've specified a specification, an allowable range 200 to 300, and I've set up control limits so that if the fraction non-conforming gets more than 1 out of 10,000, I will 95% of the time get a signal by having one of these points being above the upper control limit or below the lower control limit. Very nice modification of the standard X chart in this case to allow the process mean to wander more than it would if it was a purely stationary mean, but giving me a signal if, in fact, the mean wanders too far away from its long-term value. Okay. That's also a very, very useful type of chart. It's called an acceptance chart. All right. The third type of chart I want to talk about today is a Toolwear control chart. A Toolwear control chart is used for data that don't have a constant mean, but in fact have a mean that tends to follow some linear trend. This is common, for example, if the measurements that you're taking are affected by wear on the tool. which is why it's called a Toolwear chart. Toolwear charts are used to determine whether or not the mean in the measurements is changing at a constant or expected rate. We can also put specification limits on our Toolwear chart to help determine when the tool should be changed. Now, I've taken a sample of data from the very well-known book by Duncan on industrial statistics. In this particular case, they were using a tool to produce a part. And every hour, once every hour, they took 5 samples and measured the diameter or whatever it is they were interested in on those particular samples. They expected, because they were using a tool to create these items, that there would be some change in the measurements over time. And you can see that in general, as we go from hour to hour in this particular data set, that there is a linear increase in the measurements. Now, there's also a specification for the item, for the measurements. The specification is 0.255 to 0.265. What we would like to do is we'd like to create a control chart for this data. But the control chart is going to have to take into account the fact that we expect the mean to change as the tool wears. Now, let's have a little bit of new notation. Let's let xtj be a measurement that we take on the jth sample at time t. Our model is now going to say that the observation at time t, the jth observation, will be equal to alpha plus beta t plus epsilon, where alpha plus beta t is the mean of the process, and again the epsilons are assumed to be NID 0 sigma squared. This basically changes the normal model such that instead of being a constant, the mean follows some linear trend. Could go up, could go down, but it's not just a constant mu. Okay, well, let's see what kind of control chart we would use for this particular data. So let me go back to Statgraphics here and open up a data file called Toolwear. Now, what you can see is they took samples every hour. They took samples at 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock, and so forth. And in this case, they actually took and measured 5 samples every hour. Now, the first 2 sets that we looked at, first two sets of data, were individuals data. This data comes in subgroups. To create a Toolwear chart for the data, then, I'll go to SPC, Control Charts, Special Purpose Charts, and here you see the Toolwear charts. We have one for group data, one for individuals data. I'm going to pick this time the one for group data. The columns X1 to X5 contain the measurements. Time will be used for the x-axis. The specification limits are 0.255 to 0.265. They're not involved in the control limits, but they are useful to put on the chart. Let's just take the defaults. Well, what choices do I have? Well, I can do either an initial study, in which case the program will fit a line to the data, or if I did a control to standard, I could specify my own intercept, slope, and sigma. I'm going to leave it though on initial study. I can estimate sigma in two different ways, either from an R or S chart, which is the standard way to do it, or from the model mean squared error. What that would mean is that it would fit a linear regression model and use the mean squared error to estimate sigma. I also have the option, if I want, to include model estimation error. That would be errors in estimating the intercepts and the slopes. In control charts, we normally assume the model error is very small compared to the actual process variability, so I'm not going to check that. As usual, I'm going to take all the defaults, and now you see a standard Toolwear chart. And actually, I'm going to do two things. I'm going to go to pane options, ask for a few more decimal places in my limits, and also ask for my spec limits. What you're seeing here is the mean measurement at 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, and so forth. It's fit a linear regression to the data, and at each location where you have data, it's added plus and minus 3 standard deviations to the mean. So it's the line plus and minus 3 standard deviations. A out of control signal would occur if any one of these blue points were to be outside the upper control limits and the lower control limit. And of course, the upper and lower control limits are changing as a step function, staying in line with the change, the linear change in the mean. Okay, so that's a control chart that you'd use if you thought your mean had some linear trend, was either going up or going down, and you wanted to be sure that it was going up at or down at a constant rate. Okay. Those charts have been around actually a long time. They're called Toolwear charts. Now, the fourth type of chart I want to look at is new to version 17. The other charts I'm talking about today have been in Statgraphics for many years. These charts, the fourth type of chart, though, are new to version 17. And they are charts for rare events. We've added actually 2 new charts to version 17, a G chart and a T chart. They're very useful for monitoring events that don't occur very often. Things like hospital infections, factory or mining accidents, unexpected shutdowns of a power grid, something like that. The 2 primary charts are a T chart for events if we record them over continuous time, or a G chart for events recorded in discrete time. Now, I've brought along 2 sample data sets, both having to do with the occurrence of infections in hospitals. And I'm going to load this data set into Statgraphics in just a moment. The first column is called infection time. You can see it's a date-time column, and what it records is the time to the nearest minute when an infection occurred in a hospital. This is a record of events that occur in continuous time. The second column, which is unrelated to the first, I just put them in the same file for convenience, records only the day on which an infection occurred. It's not as precise as the first. It doesn't record the actual time. It records just the day on which an infection occurred. And you will notice if you look at the second column that there are certain days, like January 14th, for example, when more than one infection occurred on the same day. Okay, we would like to create a control chart for these data, basically to monitor whether the occurrence of infections is constant, that infections are occurring at a constant rate, or to catch cases when they start to occur more frequently. Now, some things that make this problem interesting are that because the events are rare, if we try to use something like a C chart, we'd find out, for example, if we plotted the number of infections every day, that we got lots and lots and lots of zeros. And it wouldn't be that helpful in terms of detecting case situations where the infection rate increased. A better approach, if you have rare events, a better approach than plotting counts is actually to plot the times between consecutive events. How long has it been since the last infection occurred? And we know certain things. We know that if we're recording events over continuous time, that the inter-event times are typically well modeled by a Weibull distribution. On the other hand, if we're recording events only to the nearest day in discrete time, then the inter-event times are likely to be modeled by a geometric distribution. So we can use a control chart based upon the Weibull distribution or the geometric distribution to monitor these rare events. Okay. Well, let's go look at some data. Let's go back to Statgraphics, and I'm going to call up these couple data sets. I have them in a file called infections. Here they are. There are two columns. The first column has infections recorded over continuous time. The second simply records infections to the nearest day. To generate a control chart for the data, I'll go to SPC, Control Charts, Rare Events Control Charts. We have a G chart for discrete time events, a T chart for continuous time events. So let's go to the T chart and start with the first column, infection time. Now I can actually put the data in two different ways. I can put in either the time of occurrence, that's the way I have it in this data file, or the time between occurrences. How many minutes has it been, for example, since the last infection? It's going to make a control chart for the time between occurrences. But for convenience, you can put in the time of occurrence like we're doing here, and it will calculate how long it is between consecutive events. So I'll put in time of occurrence. That's how my data are recorded. Standard options, we either do an initial study or a control to standard. I'm just going to take all the defaults, and here is my T-chart. Now the T-chart plots, as you can see, the time between events. It has a lower control limit, in this case of 101.75 minutes, an upper control limit of 8,059 minutes. The control limits are based upon a Weibull distribution. You can see up at the top the estimated shape and scale parameters of the Weibull distribution. What I'm looking for typically here is times below the lower control limit. If I see a time below the lower control limit, it would mean that the time between infections has now gotten unusually small. Right? And if the time between events gets unusually small, it's an indication that the infection rate may have increased. This data set actually looks okay. All the points are actually within these 3 sigma limits. I'll call them 3 sigma. They're based upon the Weibull distribution. Maybe we should call them 99.73% limits. Or I'll call them, how about this, equivalent 3 sigma limits. They contain the same probability that plus or minus 3 sigma would if in fact you had normally distributed data. So this data is okay. It does look to be in a state of statistical control, no points beyond the control limits. Now let's do the discrete data. Let's go to SPC, control charts, rare events charts, G-chart. The second column, called date of infection, has the infection times recorded only to the nearest day. And because of that, I'm going to use a G-chart. Same options for this, same options coming in. The only difference if you have discrete times is that we'll be using, instead of a Weibull distribution, a geometric distribution. And you see, as before, a lower control limit and an upper control limit. You see the mean time between events was about 3.9 days. The chance of getting an infection on any given day, about 0.2. Now there is one problem, one detail that you've got to watch out if you're doing a G-chart. And that is, you may notice that the lower control limit is 0. That means it's impossible to be below the lower control limit. Now that's unfortunate, of course, because the lower control limit is the control limit I'm really interested in. You can see, in fact, there were quite a number of zeros. 0 time between events means that the infection occurred on the same day. Well, what happens, and the only way to make this chart really useful, is to add a run rule. Okay, if I look at the runs tests for the G-chart, you will see the standard test that we use for most control charts to signal unusual events. 8 in a row above the center line, 8 in a row going up or down, 4 out of 5 beyond 1 sigma, and so forth. You'll also find a special rule just for the G-chart. It will signal an unusual event if it sees 4 or more consecutive zeros. 4 or more consecutive zeros has a probability of occurrence of about 0.27%. Actually, if you go to analysis options, if you go to pane options, you can set the probability. There's a consecutive zeros test. If it sees consecutive zeros, lots of zeros in a row, and the probability is less than you specify of that occurring, it'll give you a signal. And you can see that that's actually happened right in here. Right in this little section here, there were 1, 2, 3, 4, 5 zeros in a row, which would have set off an alarm indicating an unusual occurrence. The infection rate appears to have been unusually high on that particular day. Very interesting chart if, in fact, you do have rare events that you'd like to plot. Okay. Those were the T-charts and the G-chart. Okay. One more quick chart to show you that I think you might find useful is something called a Cuscore chart. Now, don't confuse this with a Q-sum chart. This is different, although it will, in fact, contain a cumulative sum. A Q-score chart is a chart that George Box and some of his colleagues developed, which is designed to detect a specific type of disturbance. Let's suppose, for example, you know that when your process goes out of whack, that something in particular happens, that it'll spike up, or the data will go up as a ramp, or maybe there's a step change, or maybe a sine wave appears in the data. A Q-score chart is a chart that's designed to detect a particular pattern, a particular disturbance in a set of data. Now, I have an interesting data set that I made up a couple days ago. A data set consisting of noise plus a sine wave. Actually, here's a plot of my data. I generated actually two columns of data. I generated a column called noise, that's the blue points here, which were randomly generated from a normal distribution. I then generated a second column, which was 0 for the first 100 time periods, and then for the next 100 time periods followed a sine wave with a specific period. Let's suppose I know that when my process starts to fail, I always start to see a sine wave with a period of 100. I can actually construct a Q-score chart specifically designed to pick out when such a sine wave occurs. Now, incidentally, here is a picture of the signal plus the noise, the two added together. That's the data that I'm going to see. That's the data that I want to chart. And I want to create a control chart that's best designed to pick that sine wave out of the noise. Now, I'm going to give you just a real brief discussion of what the theory is, and I'm going to point you in a moment to a good text to read about this. What a Q-score chart does is it plots something called a Q, the letter Q, score. Q at time t is actually defined as the sum up from time period 1 to the current time period t of a hat sub I times r sub I. The r sub I values come from a very special detector time series that the references I'll point you to show you how you can construct. The a sub i's are the residuals from an ARIMA model constructed in the same manner that we did for our ARIMA chart earlier today. We plot these Q scores, we put control limits around them, and if Q goes outside of those limits, it indicates the presence of that specific disturbance that it was designed to catch. Okay, let's go ahead and do this, and then I'll point you to the reference. Let me go back now to Statgraphics again. I'll go to File, New, and then I'll open up a final data file called Signal plus Noise. Here's the noise. That's random normal deviates. Here's the signal. It starts out at 0 for a while, and then you see the sine wave. to create a Q-score chart, you go to SPC, Control Charts, Special Purpose Control Charts, in this case, Q-score Individuals Chart. The data I want to chart will be the signal plus the noise. Now, normally you won't have, and I need to spell this right, you'll only have one column of data. You'll have the signal plus the noise already. You won't be able to separate them. But for convenience purposes, to do this illustration, I've generated them separately. Anyway, we're going to plot the signal plus the noise, and I'll put in T for time. On the Analysis Options dialog box, I will specify the signal I want to detect. Do I want to detect a spike, a ramp, a bump, a step change, an exponential increase, a sine wave, or even a custom pattern? I can put in a pattern of up to 12 values that I want to detect. In my case, I'm going to tell it I want to detect a sine wave of period 100. Over here, I can specify an ARIMA model. If I leave it at 0, 0, 0, that's called white noise. That's just normal independent NID 0 sigma squareds. We'll take the defaults going in, and it will create our final control chart of the day, a Q-score chart, where it's plotting Q versus time, like a cumulative sum, but a little bit more complicated, with specially designed upper and lower control limits that will detect the presence of a sine wave, in this case, with a period of 100. And you can see that this Q statistic remained quite close to 0 for the first 100 time periods. And then when the sine wave kicked in, Q started to go up, 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 until that period, what period is that? About 126, the Q series went outside the upper control limit, and it would have signaled out of control. I've detected that sine wave. Do what you need to do to fix the process. Okay, well, those are 5 very interesting types of control charts, less widely known than some of the others, but also they all have very nice applications. I want to point you to some important references. The primary reference, if you're interested in these kinds of control charts, is the book by Doug Montgomery. It's called Introduction to Statistical Quality Control. It's in its 7th edition, and he has examples of every one of these special types of control charts. That would be my primary reference if I was you, to get all the mathematical details underlying these charts. I also wanted to reference, though, a very famous book on quality control in Industrial Statistics by Atchison Duncan. The original edition of that dates back, I believe, into the 50s. But it's interesting. You'll find Toolwear charts, acceptance control charts, and so forth, even in some of the early editions of his book. And then finally, the primary source on the Q-score control charts, if you really want to get all the details behind that, is a book by Box, Luceno, and Del Carmen Paniagua Quinones. I probably butchered that name. But it's in its 2nd edition right now. It's called Statistical Control by Monitoring and Adjustment. So those 3 references are quite useful in seeing all the details behind what I talked about today. Now, if you'd like a copy of my presentation, or you'd like to view the webinar again, you can go either to www.statgraphics.com, click on Learn and then Instructional Videos, or go to www.youtube.com and search for Statgraphics control charts. You'll find, let's say by Friday at least, a recording of the webinar. You will also see some other videos I've done on these various types of control charts. Okay, I hope you found that useful. And now I'll take a look and see what sort of questions I may have gotten. Okay, it looks like I've gotten quite a number of questions. Let's see if I can make my screen a little bit bigger here where I can view these questions. It gives me about one line at a time. Okay, the first question that was sent to me, it says ARIMA chart questions, say financial data, ratios, etc. Can I use regressors in automatic forecasting to lower the RMSE to get the right model as I do if I wing it with no regressors or adjustments like inflation, etc.? Okay, the automatic forecasting procedure, as I talked about it today, was just used to help me pick an appropriate ARIMA model for the ARIMA control charts. I believe it's possible in the automatic forecasting procedure to do various types of adjustments. I'll have to go back and look at that. That's actually not within the scope of the webinar. I'll tell you what, I'll try to schedule a webinar though on the automatic forecasting procedure, and then we can look in detail about what the options are there. As far as the ARIMA control charts are concerned, the only use of that automatic forecasting procedure was to determine what sort of ARIMA model I needed. Okay. Second question, what is long-term in ARIMA models? Well, in ARIMA models, you would consider long-term to be a long enough period that the correlation between observations at either end of that period had gone effectively to zero. When you have a dynamic process, for example, as we had with that concentration, there is some correlation between observations, 1 minute apart, 10 minutes apart, 20 minutes apart. But once the observations get far enough apart, let's say 8 hours apart, that correlation has totally disappeared. If I talk about long term, I'm talking about a long enough period that the correlation between the observations at either end of that period has dissipated, is gone. It's a relative sort of term. Short term means close together enough that the observations are correlated. Long term means far enough apart that the observations are not correlated. Question 3. Must all of the observations within the ARIMA model be within the 95% guides? Or can they be close? Well, anytime you're plotting a time series, you're making lots of plots. Expecting all the observations to be within 95% limits is not likely. Right? If you plot 20 observations with 95% limits, you expect one of them to be outside the 95% limits. That's why, for example, when we do a control chart, we don't use 95% limits on a control chart. We use 3 sigma limits on a control chart, which are essentially 99.73% limits. That's because when we plot lots of data, right, we know 1 out of 20 will go beyond the 95% limits. And to keep the false alarm rates from being too large, we need to make the limits at something like 99.73%. You know, 95% limits are good if you're making one forecast, one prediction, doing one hypothesis test. But if you're plotting 100 points on a control chart, you're essentially doing 100 hypothesis tests. And you can't do 100 tests all at 95% without getting some spurious signals. Question: do the limits of a G-chart calculated by Statgraphics based on a simplified equation, or what are they based on? Well, the best I can tell you is to go to Help, Procedure Documentation. That's where we have all the PDF files. And if you go to G-chart, oh, I've got all the languages here this time. Where's G-chart? There it is. Let me call up my PDF file for the G-chart, bring it over here. There will be somewhere here the formulas that are being used to calculate the limits of the G-chart. Okay. Okay. So there's various formulas, and there is also a primary reference for you. And the primary reference, and this is the place to go to get the charts, to get all the detailed formulas. There are a couple references here by Bennion, James Bennion, geometric-based G-type statistical control charts. We took and used his results specifically in creating those particular charts. Okay. Another question: how can we build a demerit chart? Well, that's a very interesting question, and I don't know the answer to that one. I'm not sure exactly what a demerit chart is, but I'm intrigued, so I will look it up, and if it's something I think we need to add, I'll add it. Thanks for the suggestion. Another question: please talk a little about state of statistical control and what that really means. When I use the phrase state of statistical control, I mean that the measurements that I'm recording, the data that I'm collecting, comes from a distribution that's not changing over time. That the distribution from which my measurements or my counts or my rare events or whatever is coming from, that the data are coming from, is constant throughout the sampling period. If we're talking about data from a normal distribution, it means that the mean and standard deviation don't change over time. If we're sampling data from a binomial distribution, it means the probability of an event occurring doesn't change over time. Think about being in a state of statistical control as meaning that the process distribution is fixed, stationary, doesn't change over time. That's the way I think about it. Another question. This also has to do with the G-chart, or are the control limits of the G-chart derived from an inverse cumulative geometric distribution? I will have to look that up. I don't know offhand exactly where the limits come from. I'll need to read these references again and see exactly how they say to create the limits, because those are the sources that we followed in creating the G-charts. Another question, how do you exclude a single data point from a column of data that's being analyzed? You know, excluding data points is a problem for some of these charts. In particular, the ARIMA control charts, which are based on some dynamic structure, some autocorrelation, rely on having complete data. Other charts are fine with missing data. Now, typically, there are a couple ways you can do it. If I have, a standard control chart, let's close this off. If I have a standard control chart, like an X chart, concentration, let's just do a standard control chart. Control charts of concentration versus time. The best way to remove a point from a standard control chart and have it recalculate the limits is to click on a point and hit the plus minus button. If you click on an out of control point and hit the plus minus button, it will remove those points and recalculate the limits. Now, some of the charts we talked about today will allow you to do that. Some of them won't, because some of them require complete data. But that clearly is the easiest way to remove a point from a control chart. Another question on acceptance charts. If a data point representing a manufactured batch falls within the control limits, what claim can I make with regard to that batch? For example, with 95% confidence, there's no more than a 3% chance the batch fails to meet specification. Okay. The acceptance control charts that we're using here are not really designed to make particular statements about the batch. What they are designed to do is monitor the data with respect to a specification. Okay, you can see that in many cases, for example, when I did the acceptance control charts, I did it on one observation from the batch. Right, I did an acceptance control chart that was on breaking strength, right? I went to SPC, control charts, special purpose charts, acceptance individuals. At any point in time, I plotted a single data value. Now, I really wouldn't want to be doing acceptance sampling based upon a single data value. So just because I have a one point here that happens to be within those control limits, it's not like taking a full sample from the batch and making some statement about meeting the specification. Instead, it's meant typically to be used in real time to monitor the process and give you a heads up if in fact you're getting too close, at least the data that you've gotten are too close to the specification limits. So I don't believe that I'd want to make any statement like, you know, there's no more than a 3% chance the batch fails to meet specifications. I'd rather use the acceptance sampling procedures we talked about last month to make those types of statements. Another question, how do you handle the situation where an operator is constantly adjusting a process in response to a control chart? Well, that's an interesting question. If they're constantly adjusting it to keep it in control, I don't know how any of my simple statistical models here are going to work. All these models assume that there's some random component that's causing the variability that I'm looking at. If the operator is doing it, that's not a random effect, and that's definitely going to vary, going to violate the assumptions of any one of the models underlying these charts. So I don't think these charts are capable of handling situations where the operator is constantly making adjustments. And here's a good reference to a demerit chart. HF Dodge from Bell Labs. Okay, well, I will be definitely looking that up and see what I can find out about demerit charts. Incidentally, I think our last newsletter told you all that we are currently developing new procedures for the next version of Statgraphics, which will be version 18. We're in, you know, the early development cycle for that particular version. We've coded up some procedures. I'm still looking for some more suggestions from you folks, things that you really would find helpful. So please send me an email, neil@statgraphics.com, neil@statgraphics.com, things you might like to see in the next version, and we'll see how much we can schedule in. Okay, here's another interesting suggestion. What about using an EWMA of time between events for rare events, or even an EWMA chart of ones and zeros indicating an event or lack thereof? Okay, well, we could certainly take the time between events and do that on an EWMA chart. An EWMA chart typically does assume that the data are normally distributed, not that they come from some other distribution. Although there's something of a central limit theorem going to take hold that might make those limits appropriate. I'll have to think about that. An EWMA chart applied to rare events. The most common charts are the ones I showed you, G and T. I'm sure there's some other ways that we could potentially handle it. But if each point represents the next batch in a series, what can I say? Okay, I guess we're back to the acceptance chart here. Let's suppose each one of these observations came from a different batch. Well, let's think about that. If we're using the beta risk, we're positioning control limits. so that there's only a 5% chance that the batch has more than this number of non-conforming items if in fact the points are not within the control limits. So here we have an acceptance chart. I've based it on a beta risk of 5%, a fraction non-conforming of 1 out of 10,000. I should be able to say, therefore, that there is at least a 95. I got to be careful I don't get Bayesian here the way I interpret it. Okay. Running a hypothesis test with a beta risk of 5%, testing the hypothesis that the fraction of non-conforming items is 1 out of 10,000 or less. I would believe with 95% confidence that the fraction of non-conforming items is less than 1 out of 10,000. I'll go ahead and be Bayesian. Because I've set up a control limits at a 5% beta risk, okay, there should be at least a 95% chance that the fraction of non-conforming items is less than 0.0001, 1 out of 10,000. Again, I really don't feel very comfortable accepting a batch based upon one observation, but the observation is far enough apart, okay, that the probability of getting that observation, if the fraction of non-conforming items is 1 out of 10,000, is less than 5%. And therefore, either the fraction is less than 1 out of 10,000, or I got a very unusual event. All right, well, those were the questions that were submitted. I thank you for your time. I thank you for your suggestions. You've given me a couple things to look at. I hope you can use some of these charts and find them helpful. Again, send me at neil@statgraphics.com any more suggestions you have about what you'd like to see in Statgraphics. And if you want more information or you want to watch the video again, go to either www.statgraphics.com or youtube.com. That'll do it for today. Thank you very much.